Hi, my name is Eric Nguyen, and I'm a junior.
I'm Dylan Nguyen, and I'm a sophomore.
I'm T. Nguyen, I'm also a sophomore.
And unfortunately, David couldn't be here. And today we'll be representing Westminster High School on our business proposal of Superhydrophobic Perovskite solar cells, mentored by Nicholas DeMarcos.
So you may be asking, why solar energy? Well, with 173,000 terawatts of energy the Earth intercepts per year, there's a huge market for solar energy, and that's equivalent to 10,000 times more energy than the human population uses per year. Additionally, 1 billion people lack an energy source, and even more lack a reliable one. In this graph, you can see the annual energy potential for different energy resources. And as you can see, solar has the most potential. Also, this technology or this solar energy can benefit industrialized nations with high pollution.
Currently, most traditional solar panels are made of silicon, which has been stagnant in efficiency growth at 25% for the last 2 decades. It also costs an enormous 50 cents per watt of energy and is rigid in structure. However, the introduction and integration of perovskite into solar cells have seen exponential growth in the last 7 years. It is also very affordable at 20 cents per watt because it is solution made, and it is very flexible, which means it is not limited to only flat surfaces like silicon solar cells.
So what is perovskite? Well, it is solution made, and it gets its light harvesting abilities from tin or lead-based materials. And perovskite can either be polycrystalline or crystalline, where polycrystalline perovskite is usually used in solar panels. And in this schematic, you can see that when light hits the perovskite solar cell, electrons are moved to create a current. The major issue right now is that perovskite degrades with humidity. So what we're proposing is a superhydrophobic perovskite solar cell that gets its superhydrophobic aspect from nanostructured Teflon. So once we master this technique, we can connect it to portable lithium batteries or have a more efficient traditional stationary solar panel. As you can see in this diagram, we have a nanostructured material and a non-nanostructured material, in which when you have a non-nanostructured material, water can get full contact with the material. And in this molecular structure of Teflon, you can see that there are carbon and fluorine atoms. And fluorine atoms are what give Teflon its hydrophobic aspect.
To make Teflon super hydrophobic, we decided to use an oxygen plasma etching method. It's a form of nanostructuring. Immediately after processing in oxygen gas, it will become super hydrophilic. However, after we apply a fluorocarbon layer to it, it will become super hydrophobic while retaining its transparency.
So our technology will consist of 2 major components. One, we're going to have to get the solar cell and also the superhydrophobic layer. So first we have to construct the solar cell by using a process called spin coating, which you can see in that diagram right there. We will also spin coat Teflon, which would then be plasma etched and then layered over the perovskite, as you can see, and the end product should look something like that.
The biggest question when using Teflon and perovskite in union is whether one will affect the other or not. In terms of solar cell, we had to look at their absorption and transmission spectrum for both perovskite and Teflon. And with Teflon in the left and perovskite in the right. And from these 2 graphs, we conclude that Teflon has a 95% transmittance over most parts where perovskite absorbs. From this, we can conclude that Teflon will have little significance in affecting the efficiency of the perovskite solar cell.
So some potential issues. So when you plasma etch Teflon, it actually makes it super hydrophilic, which is something we don't want. To counter this, we actually put a layer of super hydrophobic fluorocarbons, and that should protect it from any water. Another issue is the spin coating inconsistencies due to the lack of fine-tuning options when you spin coat it. So this is where we turn to the roll-to-roll printing technique, where you can actually choose the thickness that you want, and it's also faster when you actually want to manufacture these. So what to expect? You can recycle the perovskite solar cells by dipping them into different chemicals to extract each part. We also expect our solar cells to have a module cost of 25 cents per watt for 15% efficiency. As you can see in the diagram with module B, it's a module that costs 10 cents, and you can see each price of the materials. We also expect our life expectancy to be 10 to 15 for each module. that is it. Would you like to have any comments, questions, or concerns?
So if I can start, I saw how you're using Teflon to protect the water and make it hydrophilic. You then said you're going to do plasma etching, and I'm trying to understand why you need the plasma etching and why it seems like one was doing something opposite of the other.
Okay, so basically what we do is to make perovskite, you have to spin coat it first, right? So once you spin coat it, you have to wait for it to dry. So a similar process when we use both perovskite and Teflon. So once the Teflon is dried, you need to plasma etch it. And once you plasma etch it, you get hydrophilic, but then that's not what we want. Once we plasma etch it, we have to also add fluorocarbons to make it super hydrophobic, because Teflon already has its hydrophobic aspect. And what the plasma etching basically does is decrease wettability or increase, in which now we want to decrease the wettability.
So the plasma, so you're going to make the perovskite and then you're going to put the Teflon on top?
Exactly.
I see. And you need the plasma etching to get it to
Yes, exactly.
adhere. Okay. Thank you.
Very good, thank you. My question is you have this spin coating to get the perovskite on, and you have the roll-to-roll printing, and those two usually aren't compatible. Do you see a way to bridge that gap in order to make it such that you can do that roll-to-roll printing, or maybe get rid of the spin coating aspect?
Well, actually, roll-to-roll is actually an alternative instead of spin coating, because as of right now, you're just doing small samples. Like in Nick's lab, they're doing small little samples. But if you were to manufacture these, you can use the roll-to-roll, which is a very efficient, fast way to add layer after layer. And that is just a better alternative because you can choose the thickness and everything you want.
Oh, yeah, yep, definitely.
Yeah.
It'll definitely make it
Much faster.
much faster, much
More
cheaper, and
efficient,
what have you.
cheaper.
Yeah.
Exactly.
So, I guess it's been shown, and there's no many major hurdles in order to achieving that goal in terms of roll-to-roll printing of the perovskite?
No, it's compatible. It's because the perovskite itself is also, it can bend, unlike silicon solar cells.
All right, thank you.
Who's going to buy this?
So we can show you right here. Dylan, you got this.
So at the beginning of the contest, our target was towards adolescents, but after surveys, we noticed that they want something that is portable and can be and utilizes solar energy, but perovskite currently right now isn't at that level. So we scaled it down. So we're trying to target industrialized nations with higher pollutions, so we can lower pollution rates.
Again, who's going to buy this? Because as a consumer, you're not going to buy perovskite to put on top of your roof. Somebody like Solar City or SunPower has to buy this, right? You need to think about what your markets are. And it's not industrialized nations, and I don't think it's consumers at home. So I want to nail you down on who you think your buyers are, or where the value added here is.
So would you license it out to an existing solar company? Take the idea to them and allow them to
that's
run
the-
with it?
That's our goal.
Can you tell us how you came up with this idea?
So we were actually inspired because I'm a junior, and I actually came here last year for a presentation that Nick gave. And his presentation was on the perovskite solar cells, but they had one issue. They degraded with water. And so we wanted to find a way to improve on these solar cells, so we thought we would turn to super hydrophobic alternatives. And so we thought we would combine both these technologies to come into like one big product that we can utilize in this, today's world.
Thank you for your time.